about a particular sort of symmetric circuit that has sort of dependent sources in it. And typically people don't go into too many of these conversations where you have both things, but it turns out it's a very rich set of concepts, and it's also a very rich structure in terms of how these typically get done. If you look at the circuit over here, for those who've done some advanced related circuits on this, you'll immediately realize this is a typical small signal model you might imagine for a typical differential pair amplifier. And so it's a very real thing, and it's sort of very typical where you would use these kinds of techniques and these sort of various techniques to kind of use symmetry in a physical circuit, in particular in a linear circuit. So if you're looking at such a circuit and you kind of think, I wonder what I'm going to do with this. And you think, well, where is the symmetry? Well, one of the first things you realize right off the bat is that this R0 can actually get split into two R0s, right? Two R0s, two in parallel. And that's what you get. So it does actually allow you to have a point of symmetry and cut right down through the middle of the circuit. You think, okay, that works out pretty well. So that means I can then talk about I have a whole circuit on the one side and a whole circuit on the other. Well, remember what we're doing with these differential circuits is I'm going to be applying two inputs, which in this case is V1 and V2. I'm going to be applying the same voltage to them, and then I'm also be applying a voltage that's going to be moving opposite to each other. So a common mode, or a sort of average, everybody's at the same voltage, and then one where everything is completely different around some sort of DC level. And I'm going to solve for both of those two cases, knowing that I can decompose any signal or any sort of input into a linear combination of the two of them, two things, in this case sum and difference. And then I can solve the circuit for the sum case, I can solve the circuit for the difference case, and then simply just add things together when I'm all finished. Well, that's certainly going to work out fairly well. So that's kind of what we're going to look at here. And so when you kind of look at this particular structure, we'll have a sort of differential mode case and a common mode case. So you think, okay, well, how do I begin to look at this? Well, remember the first key thing is that the point of symmetry is critical. And first you identified, and here we have one node of symmetry. And what you see with the one node of symmetry is that that particular node, when I have all the inputs are the same, I'm going to expect when all the inputs are moving up and down exactly the same, what am I going to get? Well, it means that I'm basically going to have everything balanced, and there's going to be no current going between the two pieces. So as a result, I'm basically going to have an open circuit there. And so that actually says I can sort of take this whole piece of it with the R0 and basically sort of break this connection. Well, this kind of gives you the circuit I have here, where I'd have this for VB. I can then also do the thing on the differential side. Maybe I'd probably take this side because I can look at V1 has the positive VD in it, and look at what would be the output here, which could be VA or VB. I labeled it as VB in this case. I probably should have been set as VA in this case. And then you can actually say, well, what does that look like in terms of differential signal? Now, of course, you could be putting plus or minus either way, so you could swap that. So that kind of works, as long as you keep everything consistent. And so what you get, though, is this rather large circuit breaks into two things. Now, how does this one form? It forms from the fact that the point of symmetry, the node of symmetry, ends up being at ground. Okay. And so as a result, the node of symmetry then is really this point V, and this becomes ground. And you think, okay, well, that knocks out the resistor, but it also knocks out this dependent source and this one because they're both dependent on the same voltage. And so then when I just kind of cut through it, all I end up getting left with is this current source and this resistor. So it becomes a very simple circuit. You can look at the current that goes through the loop, which is just this GMVD. That's the current that pulls through here. It's pulled in the negative sense, so that gives me the negative sign on that current, and I go from there. So it works out fairly straightforward way to solve this one. This circuit takes a little bit more in terms of its solution. What you end up needing to do then is you realize that the current that's going through this resistor is the same that's coming up through this resistor, and that's going through these two sources. So in equations saying exactly what I just said is I've got V over 2R is equal to the current that's going down through those two current sources, so the GM and the GS term, and then minus VB over R1. And that gives me my terms. And you're thinking, okay, that's not too bad, because I can get this first equation out of all of this, which works out extremely well. And then I can just basically take the first and third terms and get the additional term in terms of what does VB look like as a function of V. And this allows me to solve this equation directly. So the first one here is actually kind of useful. Notice that we've got GS plus 1 over 2R0. So in this particular case, what you find is, which one is bigger, which one's smaller? Well, typically in the way these numbers are used, GS is going to be much bigger than the 1 over R0, so I can kind of let that go. Of course, I could just solve it directly with the full analytics there, but then I know I have that. My solution for VB as a function of R is going to be related to R1 over 2R0. So that comes off that term. This term falls into that space. And as a result, I get my solution here, which is basically a little less than a gain of 1 in 1,000, so a little lower than that, which is really, really useful because you would expect if you're having a structure that is kind of thought of as a differential amplifier, you'd expect that you should get a decent gain for a differential signal, say gain of 5, but I'm also then going to get a very low gain for the common mode signal. But I would also say that if, again, you have a circuit like this, it's really amazing how the symmetric circuitry allows you to break this into very, very simple pieces in such a circuit.